Hello folks, Chandler here to talk today about momentum and collisions. Today's notes will be over part one of this unit, linear momentum and impulse. So let's get right into it and look at our learning goals. Today's goals, we're going to find out what is impulse, what does that word mean, as well as momentum, when and how can we use it, when are the circumstances when we're going to want to use this tool to attack a problem. What are the relevant equations for momentum and impulse? What do the graphs of force, time, and momentum tell us? We'll see some multiple graphs here at the end, and we want to make sure we remember what those graphs tell us about these three relevant things: force, time, momentum, impulse. Not more than just three, I guess. Okay, so let's define some terms. First, we have linear momentum, as we discussed in the lab. Linear momentum is p. It is a vector quantity. It's defined as its mass, an object's mass times its velocity. Simple as that. Very simple equation. Of course, you know by now that it can get harder and more complicated, and we'll see some of that stuff later. But that's pretty much it for now. It's just m times v. Momentum is a vector quantity. It has the same direction as the velocity, so it's very important to always consider the direction of momentum. As again, in our lab that we just did this week, we talked about how when we had two objects that were moving away from each other, like these are the cards, one was to the right and one was to the left, we would say that, okay, well, this one has a negative velocity, this one has a positive velocity, so it's important that we keep that in mind as we're talking about momentum and impulse. Direction is a big deal here. Okay, and then a collision is a model. Here's our fancy. This is AP College Board's wording. I wanted to show you, and then we'll simplify things. A collision, the way they define it, is a model for an interaction where the forces exerted between the involved objects in the system are much larger than the net external force exerted on those objects during the interaction. So what are we talking about? If we think again about our carts that collided, right? We had our cart, maybe one here, and then they were colliding. Man, I cannot draw even really well tonight. And this cart was going to smash into this cart, has some velocity towards that cart. The forces between each other, right? When they bump into each other, they're going to apply a force to each other, right? Newton's third law says, and the reaction equal to reaction. So they're going to apply forces to each other. And those forces they apply to each other is way, way bigger than any other external force going on, like more than gravity, right? The net force of gravity and the normal force are canceled out anyway. And so there's no other real forces going on. So a collision is when we talk about the forces that are exerted between objects, and they kind of dwarf any other forces that might be happening. In fact, in this level of physics, in this class, we're going to talk about only collisions happening within a system. So in our lab, we called our two carts the system, and so that was actually an internal force. The two cars colliding will be internal, and we're only really ever going to talk about problems like that at this level of physics. Okay, so internal forces colliding, and we talked about how there are three different types of collisions in this class: collide and bounce, collide and stick, and explosion. Let's derive impulse. So it's important sometimes to see where these equations come from. So we know that Newton's second law says that acceleration of an object equals the net force divided by the mass. Yeah, man, this pen is really not cooperating. Divided by the mass. And we also know the acceleration of an object equals the change in velocity divided, let's write it this way, it's the final velocity minus initial velocity divided by the time. And if I were to replace acceleration with this expression instead and rewrite it that way, I'd have Vf minus Vi over time, and that equals force. I'll just use F over M here, forget the net symbol for a minute. And I can rearrange this a little bit. I'm going to multiply M over this side and the T this side, so I'm going to cross multiply T here and T here, that they'll cancel on this side, and I'm going to do times M here and times M here, and these M's will cancel, and end up with the equation looks something like this. I get force times time equals the mass of an object multiplied times the velocity final minus initial. And we remember that momentum, if I were to kind of multiply the m by both of these terms, I guess I could rewrite this differently and just call it this first, just for a second here, although we don't formally write it this way usually. Right, that I could say this: it's the f times t quantity here. It's force times time equals the mv final minus mv initial. Well, m times v is momentum, right? We talked about that. So this is mv final, momentum final, minus mv initial, momentum initial. So it's a change in momentum. So this f times t quantity is what we're going to call impulse. And we usually leave it written like this. All right, and get rid of the arrows here. All right, so just like that. So this term ft right here, we're going to call that j, and that is what impulse is. This j equals, two different ways you can write it. We can say it's f times t, or we can say j equals m times vf minus vi. And now you see where that comes from. And sometimes we write it this way. We say, you know, we might have to use that equation where we put both of those together. But j is the symbol for impulse, and it is defined as the quantity of force times time, right? So Newton seconds, how long are you going to apply a force to an object? You're going to apply a force really, really fast, like just a second or two, or maybe for like over a long period of time, right? How long are you applying that force? And the more you apply that force, the longer time you apply it, the more momentum is going to change, right? Because look at this side of the equation. Remember, that side means change in momentum. So our simplest definition of impulse is just a change in momentum, which is why I have it written over here. Change in momentum. That's what impulse is, right? Okay, so that's our definition. That's how we derived it. Let's look at an example of impulse, right? So here's an example of what I mean. Up until this point, we've only talked about, constant forces. I'm going to go back to this. And by the way, I just want to say one thing about this. The F in these expressions is really F hat. This is average force. Okay, we're only going to have, at this level of physics, in AP1 and algebra-based physics, we can only talk about constant forces. So we're not going to have any kind of problem where we have to do math, where we're going to have a force that's changing, right? Like it increases and then it gets smaller again, right? We're not going to have problems like that with the mathematics. We might have conceptual problems like that, but not mathematic problems. So this is the average force applied. And let's get an example so we can see what we're talking about. So here's an example of impulse. Is this tennis ball is going to collide with this racket. Now, again, up to this point, we haven't talked about how long, last semester I talked about pushing boxes up a ramp, or pushing a box across the floor, or pulling a rope, right? We never talked about, well, how long are we applying the force for? And now we're going to do that. And when we look at this tennis racket hitting this tennis ball, we're going to notice that the moment they come into contact, some interesting things happen. This is a super slow motion. And we'll notice that as soon as the racket makes contact with the tennis ball, watch the tennis ball's center of mass, where my mouse is, you can see that. It actually doesn't move right away. Watch. As soon as it makes contact, right here, center of mass isn't moving. The tennis ball is going to compress on one side. It gets all squished up. And then its center of mass really still hasn't moved. And then as the momentum is transferred to the tennis ball and the force is applied over a little bit longer period of time, that tennis ball regains its shape, kind of uncompresses in a sense, and then is shot out and bounces off of the tennis racket. This happens so fast that we can't see it with the naked human eye, but this is how all collisions happen. Objects collide. They both usually will compress to some degree and kind of squish and distort their shape, and then reemerge, regain their shape with that elasticity, and then they'll bounce off. And while they're in contact, right, they're applying forces to each other, and there's momentum that's being transferred, right? So this is what I mean by an example of impulse, right? Because this force is being applied. We're transferring momentum from the racket, right, to the ball, right? And really, we're transferring in both directions. We'll talk more about that later, but it makes most sense right now to think about it in that way, I think. From the racket to the ball, and we can see how the collision takes place over a period of time. The ball gets squished and bounces off. So we might, this is clearly a collision, right? The tennis ball and racket colliding. We might use impulse to analyze a problem like this. So this is one example of what I mean by a collision, and we could use impulse to describe that. All right, so the definition of impulse, like I already said this, so let's recap it. So J is impulse, and this is equals a change. God, this pen is just awful. Equals a change in momentum. And we had those other equations from the last slide. They gave us several ways of defining that. All right. So the gist of this is, again, recapping that impulse, right, is a force applied over a time period that tells us how much momentum we're changing the object, right? If I hit that tennis ball really hard, I might, if a tennis ball goes flying off at 100 miles an hour or whatever, clearly I gave that tennis ball some momentum. Now it has velocity, has mass and velocity, right? And so I transfer momentum from the racket to the ball, right? By applying a force over a period of time. Okay. All right. I want to talk about the relationship between force, time, and impulse. So we have this equation, J equals Ft. Actually, I'm going to change this a little bit. Let's go with the original equation we had, which is Ft. This is impulse on this side, right? Equals m, and then Vf minus V initial. Now, let's look here. I have a list of some common momentums of different objects. You'll see a falling raindrop has a momentum if it's going at that speed, and has that mass of 0.0001 momentum. By the way, the momentum units are there, kilograms times meters per second. There's no special word for it like newtons or anything. It's just kilograms times meters per second. A bullet has a momentum of 2, 4-gram bullet. Pitched baseball, a momentum of 6. It's going 40 meters a second, which is about 100 miles an hour. Maybe actually it's faster than that. I'm not sure, actually, but it's pretty fast. Running person, car on highway. Okay, so here's what I want to talk about. There's one of the biggest misconceptions in this class, in this unit, I mean, is students want to think wrongly that when an object is applies a force to something, right, to transfer the momentum, that the impulse will change depending on the force or time. Let me give you a better example. So you know what I mean, right? Let's look at the next slide. We can look at this slide for a second, actually. Let's look at the pitch baseball, and I'll compare that to the bullet. All right, now, if I throw a baseball at you really, really hard, it's gonna hurt, right? It's not gonna feel good, especially if I hit you in the face or something. I wouldn't do that. But let's say, throw a ball at you, hit you in the arm or maybe the back or whatever, and it hurts. It's not gonna kill you, not gonna break the skin probably. It's gonna leave a bruise, maybe a mark. It's not gonna feel good. The bullet, though, that's gonna pinch at your skin. Obviously, I shoot you, you got shot with a gun. I mean, that's not good. You're gonna bleed. You could die. I mean, it's awful. But look at the different momentum. The momentum that a bullet carries is only 2, an average, 4-gram bullet, small bullet, compared to a baseball. Here's my question: how can a bullet do more damage? How can a bullet penetrate your skin and cause internal damage to your body? Baseball can't do that. If the baseball has more momentum. All right. So here's the thing. This is what I want to pause the video if you want to think about it. All right. Here's the deal. Right. Let's say for a minute that let's change the numbers up. Let's say that the bullet does. Let's make it's a heavier bullet. Let's increase the size of the bullet so that the momentum of the bullet is actually 6. All right. So if they have the same momentum, right? So here's the bullet. God, I cannot. This pen pad is just awful. Here's the bullet. Okay, whatever, you get the idea. And it's gonna go at you. Here you are. Okay, and then here's a baseball, or whatever, and it's gonna be thrown at you, and there you are. Okay. Now, when the bullet hits you, now look, they're both going to deliver 6 kilogram meter second of momentum to you, right? Let's say you're standing still, so your momentum is 0. The bullet is going to hit you, and the bullet's going to go into your body and then stop, right? Same thing with the baseball. It's thrown at you. Baseball is going to go at your body. It's going to hit your arm or whatever, and then the ball is going to stop, right? So the momentum initially of the system, bullet plus your body, is 6, and the momentum of the baseball initially in your body is also 6, right? We change the numbers just to make it easier, okay? If the momentum initially is 6 in both cases, then why does the bullet penetrate your skin and the ball does not, right? What's the final momentum? Well, in both cases, if the bullet stops, right, the final momentum, and you're just going to stand there and take the shot, right? So at the end, the system's momentum is 0, and at the end here, system momentum is 0. So in both cases, a projectile is launched at you, baseball or bullet, with 6 units of momentum. It hits your body, and then we have no momentum afterward, right? Friction probably takes it all away, dissipates the energy, whatever, okay? But in one case, you got hit with a bullet and are now could be bleeding and dying. And in one case, it's just a baseball, and yeah, it hurts, but it's not going to kill you, okay? My question is why? If they're both delivering the same amount of momentum, mass and velocity and all that, then how come one can kill you, one just is going to hurt and leave a mark, but not be that big deal at the end of the day? here's the thing we have to consider. J equals Ft. All right. Here's the thing. When a bullet hits you, how long is it in contact with your skin for versus the baseball? Think about the material of a baseball and the material of a bullet. Bullet's made of metal. Baseball's made of leather and other actually some weird stuff you might not realize, like rubber in the middle and some string around the edge and leather outside. It's softer, right? It's gonna hit your skin, and it's going to compress like the tennis ball, not as much, but still some, and squish and then bounce. And the time that the baseball, and is your skin or in contact is going to be much larger than it will for the bullet. But remember, the momentum that they're both carrying is the same. So the impulse, the change in momentum, right, goes from 6 to 0 in both cases. So in both cases, this impulse is the same for both scenarios. Bullet hitting you, baseball hitting you, the impulse is the same from 6 to 0. Our change in momentum was from 6 to 0. But the time for when the baseball hits you goes up. Okay, now think about it. This relationship. If the time goes up, but the J has to be the same, what must happen to force? It's got to go down. So the force you feel when the baseball is less. The impulse is the same. They both deliver 6 kilograms per meter second of momentum. But because the bullet impact is made of metal, it's not going to squish and compress, it's going to penetrate your skin. The impact time is much smaller, it goes down, so the force it delivers is greater. It's like they're both carrying a bucket of water, right? The bucket of water is the momentum in this example, okay? And in the baseball's case, it's going to deliver that momentum slowly over time. So it can just kind of pour it out slowly, right? It kind of trickles the water out of the bucket. The bullet, it has to deliver the same amount of water, momentum, but it has to do it really, really fast. So it's going to just dump the bucket all at once. All the momentum, bam, here you go, all at once. So the force it applies is way higher than the force that you're going to feel from a baseball. Well, baseball's going to hurt, but still not as much as the bullet's going to hurt, right? So that's the relationship we have to see. So many problems we're going to see in this class, in this unit, the impulse is going to be the same, and these two numbers are going to change. And we have to recognize that as the time goes down, force goes up, and vice versa. Okay, I think I said that enough. Here's another example, car crash, test dummies. Some of them are wearing seatbelts, some of them are not. On this one, they're not. The ones on the far side are wearing seatbelts. You see how much safer that is. But again, why do we wear seatbelts? In both cases, where they have seatbelt or no seatbelt, their initial speed is the same, and their final speed is the same, 0, right? Eventually, they're going to come to rest, right? Well, then why do the people in the airbags, live and the seatbelts live, and one without is, getting destroyed? Well, because the time of impact, right? If we wear an airbag or a seatbelt and we have an airbag, the time for that collision, right, is going to go way up. Right? Again, it's still microseconds, milliseconds, but it makes a difference. If time goes up, force must go down. The impulse is the same for both. You're still you're going 20 miles an hour. Oh, by the way, that video, the car was only going like 20 miles an hour. Like, doesn't take very fast speed. Wear seatbelts, people. But anyway, this impulse is the same in both cases, whether you have a seatbelt on or not. Right? So if we want the force to go down, so we don't get head injuries and and crash in the windshields, we have to increase the time. That's where seatbelts come in. So airbags come in, right? They add a little bit of time to the collision. The force has to go down. Okay, I think I've said that about 1,000 times now, so that's probably good. Okay, impulse is the average force times the time in which that force is delivered. So we already said this. So J equals Ft. All right. I forgot I put it in there. Okay. What happens when we graph the force? Let's talk about the graphs now. Okay, so time to graph. What happens when we graph the force versus time? All right. So over here, we're going to graph force versus time. Now, think back to that tennis ball problem. So if you had the tennis racket and tennis ball, and as soon as they come into contact, right, it's like they're barely touching. Just a few molecules, right, of the tennis ball and tennis racket are actually in contact. So we might say that initially the force is pretty small, right? But as more of the surface areas come into contact with each other, and the more that ball gets squished and compresses, and the more the tennis racket is pushing that ball, and they're all in more contact, you saw the video, the force is going to go up, right? Up, to a point where the tennis ball then starts to bounce off the racket, right? It starts to regain that shape, and the force goes back down, okay? and that my graph is really ugly with the idea. So most graphs of collisions are going to have some sort of curve shape. Sometimes we'll model it like a triangle, but it's usually more like a curve like this, right? So at the midpoint of the impact is when most of the force is occurring, and then after that the force goes back down because they're bouncing off each other, right? They're regaining their shape. They're no longer as much contact, and so the force goes back down. Well, look at this graph, y'all, and look over here. If impulse equals force times time, isn't the area under the curve force times time, right? If we were to model this like a triangle, which sometimes we will do, right? If we model it like a triangle, I hate to have to do this to change the colors. Let's do blue, I guess. If I model it like a triangle, I just cannot draw on this pad. Something like this, right? Close enough, okay. And we can say, okay, well, all this area here, right? This area would be the height, which is force, times time, the base, right? Divided by 2, right? Because it's a triangle. And then whatever that, well, isn't F times T impulse? So the area under the curve of a force time graph is impulse, or we sometimes say change in momentum, right? How much momentum we're adding or taking away could be negative, right? If we're losing momentum from the graph, right? So we need to remember that. Very important. Force time graph. What happened? Force time graph. Area under the curve is impulse or change in momentum. Same thing. Okay. Okay. So rearranging the impulse equation gets us this. I showed that earlier. How we got that, and then we can rearrange it again for this. Now remember, m delta v, that is momentum, right? It just our momentum could be changing. Maybe it's small at first, and it gets bigger, and so on as we increase our velocity. Whatever. Yeah. So this is momentum, right? And this is time in the y-axis. So what would happen if we were to graph momentum versus time? Well, okay, let's try this. Momentum p, little p. Oh my God, I just cannot do it. Close enough. Over time. Now look, if I were to say, okay, maybe our momentum is starting at 0 and it kind of goes like this, right? Well, so we're saying that we're gaining momentum, right? We're gaining a little more momentum and 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 a little more over time. Well, look at the equation, y'all. This is momentum in the upper in the numerator and time in the denominator. We have momentum here, right? I could replace this with mv, right? Same thing. And as our momentum increases, time is getting bigger. If we divided these two, we get what? We get force. So it turns out that the slope of this graph equals the force. And I got that from rearranging the equation for impulse, right? So here's our next graph thing. We have to remember this. And hopefully you see why this is the case, right? I know it's been quick, but still. A momentum time graph, the slope is the force, right? The average force being applied during that collision, okay? The momentum time graph is the force, okay? All right, so that's it. Summary, what did we learn? Well, hopefully we learned that momentum is a vector quantity, and its equation is P equals mv, and I should put a little arrow there to show it is a vector. It has direction, and direction is super important in this unit. As when things collide, they're going to go different directions. We learned that impulse is a change in momentum. We had a formula for that as well. Actually, we had several. J equals Ft. J is also a vector. Force is average force there, so not what it's a vector to, but also the average force. And we also learned that J equals m v final minus v initial, and we can combine those two equations to say that Ft equals mvf minus vi. We kind of just put them both together, right? They both equal J. So we can set them equal to each other if we wanted to, right? If we need to do that. What else did we learn? We learned that the momentum delivered to an object depends on the force applied and the time interval over which is it applied. So we saw graphs of force time. Oh my God, this pen is the worst. Force time, and we saw how most of the time in real life they're going to go kind of like this. But we'll get problems whether they're not. We'll get problems whether it's just a flat line or a triangle or whatever, right? But we remember that the force time graph is going to be area under the curve is going to be impulse. And we learned that, like I just said, the area under the curve is force time graph is impulse, and then we learned that the slope of a momentum versus time graph is the average force. Okay, so hopefully we are cool with all those concepts, and I was going to do an example problem, but this video's always gone way over time. Shocker, it always does. So we can do examples later, and that's it for now. So hope you have a great rest of your day, and I will see you when I see you. Bye.